So let's talk a little bit about probability distributions. This is really like the heartbeat of statistics. This kind of is what the entire field is based on, is understanding this. So let's look at these histograms. I'm sorry I drew them. They're terrible, but couldn't find a picture of it. But so for this first one here, we're looking at a histogram with a really big, like a lot of bins, right? So each bin is holding anywhere from 0 to 25, 25 to 50, 50 to 75. And then let's go ahead and shrink these bins a little bit. So now instead of being a width of 10, they're a width of 25, they're a width of 10. Still describing the same data, just making those bins a little bit smaller. As you can see, we get a little bit more shape when we do that. If we go from 10 to bin widths of 1, we're going to get something like this. And here we're going to 0.1. And we're almost approaching lines. Now, this would be much more solid than I have it, no gaps, but finally we end up with something like this nice curved. We're going to get a smooth curve out of it, where every single point has its own spot on this line. That's kind of a little bit of calculus for it, and it's really just smoothing it out, taking all those bins and shrinking them infinitely. That's why I have infinite written there. So that's how we get a distribution. I hope that helps you kind of visualize where we're seeing that. But we'll be able to take these distributions and see where data lies in it, right? We can, if this is the distribution and we know it, and we're going to pick a value from this distribution, we'll know if we're picking at random, we're more likely to pick from the middle than we are to pick from the ends. That's why we call it a probability distribution. We're more probable to pick from the region that has a bigger area under it. The area under here is much smaller, much less likely to end up there. So, here we have an example of a bimodal distribution. This is a little unique, and struggling to think of an example off the top of my head, but this is what we call a bimodal distribution. Now, on the bottom, I believe these are z-scores. Don't hold me to that, because it might not hold for this next bit, but the concept still holds if the actual values themselves do not. We end up with what is called Cheybshev's rule. This is saying that for any data set, no matter what the distribution, so this does work with bimodal distributions, with skewed distributions, we will end up with these characteristics. 3/4 of the data is within 2 standard deviations of the mean. 89% of the data is within 3 standard deviations of the mean. And 95% of the data is within 4.5 standard deviations of the mean. That's what we call Cheybshev's rule. Now, that is, that's for any distribution. But when we start to realize that we have a really common distribution, which we call the normal distribution, we can make some greater assumptions about it. We'll use the empirical rule. Because we know how this data behaves, and it behaves normally, we don't have to worry about a crazy skew off to the side or a second hump in it. We're able to make more accurate predictions about where the data lies. So here we have approximately 68% of the data is within 1 standard deviation of the mean. 95% of the data is within 2 standard deviations of the mean, and 99.7 is within 3. This is called the empirical rule. And here is an example of what it looks like. So mu, u, is our mean. Now, everywhere between mu and minus a standard deviation is going to give us 34%. Mu plus a standard deviation is going to give us 34%. Together, within 2 standard deviations, we have 68% of the data. Sorry, within 1 standard deviation. And then 2, and then 3.